Welcome back to Simplifying Synthesis. Today, we will look at the total synthesis of Aturanosides A and B. The work that we will be looking at in this video was published in Orglet by Yingjie Wang and Biao Yu. Aturanosides A and B were first isolated in 2018 by An and co-workers from a soil-derived Streptomyces strain. These compounds don't show any cytotoxicity against human umbilical vein endothelial cells, but they do significantly suppress vascular endothelial growth factor-induced tube formation and invasion of these endothelial cells. To put this simply, it means that they stop the growth of new blood vessels, which is a key step in the growth and proliferation of cancer. In addition to these aturanosides, the aglycon, which is the part of the molecule without the sugars attached, inhibits estrogen binding, which may explain its anti-tumor properties. So let's look at the retrosynthesis of these compounds. Both of these compounds could be derived from a common anthraquinone intermediate using different glycosylation strategies. This anthraquinone aglycon could be synthesized using an intramolecular Friedel-Crafts reaction of a tertiary hydroxylactone, which could be synthesized with a simple oxidation reaction. The lactone will be derived from a cyclization reaction of a hydroxyamide, which ultimately will be created using a series of alkylation reactions on a simple monocyclic precursor. So let's look at the forward synthesis. Starting off with the PMB-protected hydroxyamide, the authors carried out a directed ortho-lithiation and alkylation sequence. Reaction of this precursor with sec-butylene tetramethyl ethylene diamine and propyl iodide yielded the product. TMEDA acts to coordinate to the lithium and increases the reactivity of sec-butylene. This is directed to the ortho position by binding to the carbonyl oxygen, allowing it to deprotonate the orthoproton and form the necessary organolithium compound. This acts as a nucleophile towards propyl iodide and generated the orthoalkylated compound in an 84% yield. The next step followed an identical ortho-lithiation strategy, where again an organolithium compound was formed, directed by the amide group, and this acted as a nucleophile towards a trifluorobenzyl protected dihydroxybenzaldehyde. The authors found that using the TFBn protecting group was essential, as the more common benzyl protecting groups were susceptible to rearrangement during a later step in the synthesis. This hydroxyamide was carried forward to the next step of the synthesis without purification or isolation. A solution of trifluoroacetic acid in water was added, and the reaction was stirred for 12 hours at room temperature. This was successful in carrying out the desired lactonization reaction. Protonation of the amide increases its electrophilicity and allows the secondary hydroxyl group to act as a nucleophile and attack intramolecularly, forming a tetrahedral intermediate, which then eliminates diethylamine to form the target lactone in a 55% yield. In the next step, the molecule was oxidized to a hydroxyphthalide by first deprotonating with potassium tert-butoxide, forming an anion which readily reacted with oxygen gas to form a peroxide. This was reduced in situ by DMSO and trimethylphosphate to produce the target hydroxylactone. This was then deprotected using acetic acid to remove the PMB protecting group. This produced the target compound in an 80% yield over 2 steps. The newly installed tertiary hydroxyl group allowed the authors to carry out an intramolecular Friedel-Crafts acylation, which expands the lactone ring to produce the target anthraquinone. This reaction was carried out using trifluoroacetic anhydride and trifluoroacetic acid. The anhydride first reacts with the tertiary hydroxyl group to form a highly electrophilic trifluoroacetyl ester. This can be protonated by TFA and eliminated to leave an acylium intermediate, which undergoes intramolecular reaction with the aromatic ring to form the target anthraquinone in a 76% yield. I wasn't able to find any mechanistic studies on this type of ring expansion intramolecular Friedel-Crafts acylation reaction. So if you have any suggestions for an alternative mechanism, please let me know in the comments down below. So with the Aglycon now complete, the authors proceeded to the first glycosylation of the synthesis. This used a rhamnose derivative protected at the 3 and 4 position with benzyl groups, an acetate at the 2 position, and a thiocresol group at the 1 position. This was activated using methyl triflate to form a cationic sulfonium intermediate, which is eliminated to form an oxocarbenium ion. The acetate group present at the 2 position can react with this intermediate and form a 5-membered ring which blocks one face of the molecule. This anchimeric assistance is a common strategy in carbohydrate chemistry for controlling the stereoselectivity of glycosylation reactions, as it can be used to provide anti-stereochemistry between the groups at the 1 and 2 positions. The oxocarbenium intermediate was attacked by the phenol group of the protected Aglycon to form the first glycoside in a 95% yield, which serves as a common intermediate for Aturanoside A and B. To take this forward for the synthesis of Aturanosides A, the authors first carried out a Zemplén Deacetylation using a catalytic amount of sodium methoxide in methanol to deprotect the acetate group in a 95% yield. There has been some debate in the academic literature over the precise mechanism of this deprotection, so I have included links to papers which discuss this down below, but it can be simply thought as a transesterification reaction using a methoxynucleophile. The next reaction was another glycosylation, this time using an alkynylbenzoate donor derived from glucose, which has an azide at the 2 position and acetate groups at the 3, 4, and 6 positions. The activator in this reaction was triphenylphosphine gold triflate, which is a gold 1 salt with a high affinity for alkynes. This binds in a pi fashion to the alkyne and makes it more electrophilic. This allows for the intramolecular addition of the ester group to form a lactone together with its elimination from the sugar to form an oxocarbenium intermediate. This intermediate is attacked by the 2-hydroxyl group of the rhamnose donor to form the disaccharide, together with the protonation of the gold-bound lactone and the regeneration of the gold catalyst. This reaction formed the product in a 95% yield with an exclusively alpha configuration with regards to the 1 position of the glucose moiety. This is the more thermodynamically favoured product and was obtained by carrying out this reaction at 45 degrees. Unlike the acetate group, which we saw in the previous glycosylation, the azide group at the 2 position can't interact with the oxocarbenium intermediate and therefore does not control the stereoselectivity of the reaction. This azide group can be thought of as a protected amine, and in the next step was revealed using a Staudinger reduction. This used trimethylphosphine, which acts as a nucleophile, to attack the azide, which then forms a 4-membered intermediate. This decomposes with the elimination of nitrogen gas to form an aminophosphorane. This was hydrolyzed upon workup with water to produce the target amine and was then acetylated with acetic anhydride to form an amide at the 2 position. With this now complete, the authors moved into the final deprotection stage of the synthesis. The trifluorobenzyl groups were first deprotected using hydrogenolysis with a palladium on carbon catalyst in a pH 7 phosphate buffered saline solution. This was followed by another hydrogenolysis, this time using acetic acid, to deprotect the benzyl groups on the rhamnose moiety. The researchers were unable to find conditions which could carry out both of these hydrogenolysis reactions in one step. They also discovered that the anthraquinone ring would be reduced to an anthrone under these conditions, forming both products in a 1-to-1 ratio. However, they noticed that an NMR sample of the compound in acetone D6 auto-oxidized overnight to reform the anthraquinone, showing that it could be oxidized with oxygen gas. Therefore, they carried out the next reaction under an oxygen atmosphere. This reaction was another Zemplén deprotection to hydrolyze the acetyl esters, to produce the target Aturanoside A in a 94% yield over 3 steps. This deprotection also oxidized all of the anthrone to the target anthraquinone and left the amide intact on the N-acetylglucosamine moiety, more commonly referred to as glucnac. To produce Aturanoside B, they carried out a similar deprotection sequence, using the rhamnosylated intermediate which they had previously made. This was successful in producing the target compound in an 89% yield over 3 steps. So to summarise, the authors managed to synthesize Aturanoside B with 9 steps in the longest linear path in a 21% overall yield with a final yield of 38 milligrams. Aturanoside A, however, was produced in 12 steps in the longest linear path with a 14% overall yield of 61 milligrams. Highlights of this synthesis include the atmospheric oxidation reactions used to synthesize the anthraquinone Aglycon, the intramolecular Friedel-Crafts acylation, and the glycosylation chemistry, using the rarely used Alkynylbenzoate Glycosylation donor. This synthesis will allow the authors to produce enough material to study the anti-cancer properties in detail and fully elucidate the mechanism by which they inhibit vascularization, and could allow for the development of novel anti-cancer drugs. That's everything for this week's Simplifying Synthesis. If you like these videos, please like and subscribe, and if you have anything you'd like to see, let me know in the comments down below. Next week, we will look at the total synthesis of Atlanticone C.